Hi, T. Hi, guys. Are you hearing me? Elaine, are you hearing me? Elaine?
Yes, yes.
Okay, I'm sorry. Sometimes when I get on here, it doesn't allow me to be heard. Okay. Just one second. I'm just fixing something on my. There we go. Okay, we're doing okay, ladies and gentlemen. Elaine, you just look like you're happy to be here. I gave you Tuesday off. Okay, ladies and gentlemen. How we doing? We doing okay? Are you into thermodynamics yet? Heat law, calorimetry. Elaine, you're muted.
Yes, yes.
Okay. Bethany, where are you at right now? Hi, Kylie. Let's see, who else is here?
Sorry, we only just finished like redox reactions.
Who do you have, Bethany?
That's a great question. Professor Stodden.
You're not supposed to be doing. Are you doing chemical reactions now, Bethany? Or are you doing electrochemistry?
That's a great question.
I'm full of them today, apparently.
Honestly, I have no clue what we're doing.
Okay. Well, at least I'd like to hope that my people know what I'm doing right now. Alexis, do you know what you're doing?
With what?
Do you know what we're doing in class?
Oh, the calorimetry thing?
Yeah.
Yeah.
All right.
Yeah.
All right. At least you know that much. Oh, sorry. My hat was on backwards. How many of you have not had you got me saying it wrong, Alexis.
I don't know how to say it.
Calorimetry.
Oh, okay.
How many of you are doing calorimetry or you're kind of like, or have already done it? How many of you are doing it now or have already done it? Come on, you guys have that little button down there. Reactions. On your space bar. Click you guys don't have a reactions button? No?
Yes.
Okay, good. How many of you have, oh geez. Kristen, you just look happier as hell to be here. How many of you have done calorimetry or know what I'm talking about? I just need to have a basis of where to begin here today. That's all. I'm getting no reaction here, guys. Okay, that's fine. That's fine, guys. I'm disappointed in, let's see, who am I Jeremy or Jeremiah? Jeremiah,
Yes, sir.
you were saying you didn't raise your hand when I asked if you had been doing calorimetry?
Oh, I didn't hear that. I just joined the audio.
Okay. All right, guys. All right. Thermochemistry is the hardest part. I firmly believe it's the hardest area of chemistry to master. Thermochemistry is really the reason I am not a physical chemist today. I kind of like the area, but there's entirely too much math. Don't worry, you're only going to get the baby steps here. So right now, today, we're doing an experiment called calorimetry. Who believes you can measure? Like if you've seen those old Westerns on TV, the horseshoe that the blacksmith has in the fire, can you really get the temperature of that horseshoe? Bethany, you think you can? Can you get the internal temperature of that horseshoe? It's not like it's a steak and you can stick a thermometer in it, is it, Bethany? So basically, we have to figure out a way to get that heat by indirect methods. And basically, let's talk about heat. Okay, Jeremiah, have you ever cooked pasta?
I have.
Have you cooked it for yourself and then for like your family?
Yes.
Okay, Jeremiah, when you're cooking it for yourself, you use like a quart pan, right?
Right.
All right, and when you're cooking it for the family, you used a big pot.
Right.
What took longer to boil the small amount or the large amount? What took longer to heat up to boiling?
The large amount usually takes a little bit longer.
So would you say that the mass of the water has something to do with the heat?
Yes.
Okay.
More coverage.
Let's go. Garrus. Garrus, you out there? Thank you, Jeremiah.
Yes.
Garrus. Okay, do you take baths, Garrus? Have you ever taken a bath in your life?
Yes.
Okay, that doesn't look so now, but that was a joke, Garrus, okay? All right, Garrus, do you like, when you get into your bath water, do you like it to be boiling or do you like it to be sort of tepid?
Warm, I guess.
Warm, okay. You want it to be warm, you don't want it to be boiling. Okay, Garrus, can you tell me what is going to take longer to heat up the water? To just go to that nice bath water temperature or to go to boiling?
It's gonna take longer to go to boiling.
So the temperature difference has something to do with the heat too, doesn't it?
Yes.
Okay. I need to know somebody that cooks out there, somebody that knows something about cooking at all. Come on, somebody's got to volunteer. Okay, Christian. Do you know anything at all about cooking? Kristen?
Yeah.
All right. Have you ever seen an iron pan?
Yeah.
All right. If you felt it, it's kind of heavy.
Mm-hmm.
Have you ever cooked with it?
No.
Okay. Trust me, I have boiled more I burned more fried potatoes in an iron skillet before I learned my lesson. Okay. Has anybody cooked with an iron pot or skillet, like a Crusade or something like that, like Crusade or something like that?
I have.
Okay, good, Natalie. Thank you. I'm sorry, Kristen, but you're of no use to me right now. Good, she's smiling. It's always good when you get a smile. Okay, Natalie, when you were putting that that iron skillet on the stove, did it take a lot longer to heat that up?
I think so.
Took a lot longer to heat it up, right? All right, let me
Yeah.
ask you this. Have you ever put one in an oven?
Yes.
Did you dare touch that handle?
No.
All right, let me ask you another question, Natalie. If you had something that you were just heating up and you put some aluminum foil in the oven, okay? You heated it up, you took it off. Were you able to crumple that aluminum foil like within minutes after?
Yes.
So doesn't the type of substance have something to do with the heat?
Yeah.
So basically, guys, we are talking about three different aspects that we have to deal with. And I'm talking about the second equation down there. Okay. And I'm going to do slideshow from current slide. All right. I'm talking about the second equation here, where we've related heat to the mass of the stuff. That is the M. The S is something I'm going to call specific heat. When you were in intro, you may have seen it as C. You may have seen the equation as MCAT. I call it specific heat for a specific reason, and I'll get into that. But S is a constant that basically is determined by what type of substance you have. And that last term, TF minus T initial, is the final temperature you're at minus the initial temperature you started. Now, we have some other things that are involved here, okay? And one of them is a calorimeter. Let me see, I've definitely bothered Kristen. Maria, hi there. Jeez.
Hi.
Oh, dear God, you're smiling and bright and perky. Are you a morning person, Maria?
No, I'm not.
Compared to me, you're a morning person. Marie, have you ever put something into a thermos?
Yes.
Okay. The question I have to you is, you put coffee in there, it stays warm, right?
Mm-hmm.
You put something like lemonade, it stays cold, right?
Yes.
How does it know? How does it know to keep wait, tell me this. How does it know to keep the hot things hot and the cold things cold?
I don't know.
It doesn't. All that it's doing is it's preventing the surroundings from affecting it. It's like preventing the room temperature from warming up your lemonade or the room temperature from cooling your coffee. And basically, it does it by means of a vacuum. It has a sealed glass container in there. There's a vacuum between it and the outer wall. So there's nothing in between to transfer heat. But yet, Maria, if you put your coffee in there and come back a week later, is that coffee going to be hot?
No.
Why? This is twice I've stumped you, Maria.
I don't have my mind going yet this morning.
The reason that the coffee cools down is, to a small extent, that thermos absorbs the heat from the coffee. So we have to keep that in mind as well. Now, what we're doing over all this thing is we're talking basically about looking at a small part of the universe versus the rest of the universe. Ladies and gentlemen, Did COVID affect you? In some way, did COVID affect you? So that's an example of the surroundings, what was out there affecting COVID. Now, in the same circumstance, did you go out to party as much? Did you go out to restaurants? What is that doing to the economy? It's doing two things to the economy. One of which is you're not spending money. So you got this big pile of money. Well, not maybe big, but you have a pile of money that you haven't spent on those outside interests, right? So the demand was low. You could go to a restaurant and the prices were reasonable. Now everybody has their little pockets of money. So you go to a restaurant now, the prices have been jacked up. I love Publix. Publix is a wonderful organization. I hope you can hear the sarcasm dripping from my voice. Now, have you noticed that during the scarcity, Publix raised the prices of a few things? Did you notice that? Things weren't available, Publix jacked up the price. Amazingly, now that things are there, you notice those prices haven't come down? Gotta love Publix. In any case, bottom line, because COVID affected you, that's an example of the universe, the surroundings affecting you. By the same token, you affected the surroundings. You affected the universe. The trouble is, whatever you do, whatever happened to you, had the opposite effect on the universe. Okay? Whatever the universe did had the opposite effect on you. Let me give you an example of that. A blacksmith in an old Western takes a horseshoe, shoves it into the fire, stokes it up, gets it really, really hot, takes that horseshoe out and puts it into a big tub of water. What do you see rising out of the water? I mean, you're not there. You can't feel the temperature of the water. But what's happening to that water? Is it getting hotter? So my system, my horseshoe, got put into surroundings. It got taken out of the fire, put into new surroundings, the water. So what happened is it affected the surroundings. It made the surroundings warmer. By the same token, the water cooled it off, didn't it? So whatever is happening in terms of thermal energy, whatever is happening to the thing you're looking at, and that is basically the system. The system is whatever you want it to be. It's whatever you're looking at. Whatever happens to the system, the opposite thing happens to the surroundings. If your system gains energy, it had to get that energy from somewhere. That energy came from the surroundings. So the energy of your system went up, energy of the surroundings went down. Same token, if your system absorbed energy. So did I just do this example? I get lost in myself sometimes. System gains energy, surroundings lose it. System loses energy, surroundings gain it. So the heat of the system is equal to negative the heat of the surroundings. Do I have you all with me so far? All right, we're going to go through this. Remember, I said our heat is going to be equal to the mass It's going to be equal to some constant that's related to the media it's in, and it's equal to the temperatures. All right. We said that we can't measure the internal temperature of a horseshoe, so we can't really know how much energy is in there. But can we put a thermometer into water? We can shove a thermometer into water, right? So can we tell the temperature difference that happened to the water? We're going to use that information. We're going to use the mass of the water, and water has a very, very specific, a very, very constant specific heat, and it's very, very high. The specific heat of water is 0.4814 joules per gram centigrade. Another normal substance like aluminum has a specific heat of 0.9. Water is very, very unique. So what I'm going to do here before I start, I'm going to weigh my calorimeter. I'm going to put my water in, and I'm going to weigh my water and my calorimeter. Okay? I'm going to take a piece of metal. First experiment, I'm going to take a piece of metal, and I'm going to weigh that piece of metal. I don't know how he does it in the lab. It's been 6 months since I've seen it. But he may give you the mass of the tube and metal, and he may give you the mass of the stopper tube. If that's the case, just subtract the two, you get the weight of the metal. Or the other thing is, he may just give you the weight of the metal just straight up. All right? You're going to be given the initial temperature of the water, the initial temperature of the metal, and you're going to be given what you're doing. You're taking that hot metal, you're putting it into water. The hot metal is my system. The water effectively is going to be my surroundings. So hot metal goes in the water. What happens to the temperature of the water? Kylie?
It goes up.
Temperature of my water is going to go up. Kylie, what happens to the temperature of my metal?
It goes down.
So Kylie, when does it stop? When does the water stop rising and the metal stop decreasing?
Whenever the temperature is equal.
Exactly. What's going to happen is the water is going to continue to gain temperature until the metal reaches it. And then what we're going to do is we're going to measure the final temperature of the water. Now, there are two ways to set this problem up. Okay? You can set it up as a big, long, linear problem like this. And there's some circumstances where it makes sense to set it up like this. But personally, I feel the more numbers I get on a line, the more confused I get. So I like to do it step by step. Okay? First thing I'm going to do, I'm going to get the Q of my water. I can get the mass of my water by taking water and calorimeter and subtracting out the mass of the calorimeter. That will give me my mass of my water. The specific heat of water is, as I said, 4.184 joules per gram centigrade. The same way as R is, if you change the label, you change the number. If I want my unit of energy to be calories instead of joules, it's 1 calorie per gram degree centigrade. But joules is the official energy term, so that's the one we're going to use here, 4.184. Then I'm also going to figure out, and this is important, guys, you got to figure out in the problem where you ended up with and where you started, because it's got to be in that order when you do the subtraction. Always want to subtract T final from T initial. I do that, I get a positive 5.0 degrees. Anybody confused so far about what I've done? Making sense? Kylie
Yeah.
gave me a nod, so I know I'm good.
Oh, I had a question.
Good, Garris, what's going on?
Is the positive 5C the temperature change of the water?
Yes,
Okay.
yes, because everything here, Garris, I'm finding the heat of the water. So all of the things I'm doing on the other side of the equation have to do with whatever's happening to the water.
Okay.
All right, I do that math out. And I end up with 910 joules. Now remember, Q of my system, negative Q of my surroundings. The 910 is my surroundings. My system is my metal. So my Q of my water is equal to negative the Q of my metal. So the Q of my metal is a negative 910 joules. Now, what happened to the temperature of my metal? I started off, my initial temperature was 98.4. My final temperature is 29. So I subtract 29 and 98, I get a negative number here. Mass of my metal. Tube and metal minus tube gives me the mass of my metal. I now know what my energy of my metal is. I know what the temperature change is, and I know the mass. All I have to do now is solve for the specific heat. I do that, and I end up with a number 0.216. Now, there are charts with specific heats, and there's also this funky equation down here. I have looked, I've researched this. Somebody by trial and error came up with the number 25, and they figured out if I divide the specific heat by this number, I will get the atomic weight of my stuff. So I divide 25 by 0.216, and magically I have a periodic table at my ready, and it's 116. That's between indium and tin. If I'm a betting man, and I am, I'm going to guess that it's tin because tin's much more prevalent than indium is. That is the first part of this experiment. This is what we would have been doing on Tuesday. He may have you do 2 trials of this. At this time, I don't know. We'll go through that in a second. Anybody have any questions?
Yeah, so when you're multiplying 69.4C, should it be negative or positive?
Negative.
Okay.
So yes, you're right, Garris. This number should be a negative. Bottom line, specific heats are never negative. If you come up with a negative number for your specific heat, then you probably haven't figured out the Q surroundings versus Q system correctly. Any questions about part A and what you have to do for part A? Seem fairly straightforward? All right. Next system we're going to look at is dissolving a salt in water. Okay. Water is changing temperature. So the energy of the act of dissolving the salt is the system. So your water is going to be the surroundings, and the dissolving the salt is going to be the system. So the energy of dissolving the salt is going to be opposite the energy that the water that occurs to the water. This is a kind of it's kind of hard to wrap your mind around, But literally speaking, part of the water is part of the system and the rest of the water is your surroundings. Are we good with that, guys? Questions on that? Okay. We're going to use the same equations. So we're going to do basically some of the same things. We're going to take our calorimeter, weigh it. We're going to put water in the calorimeter, and we're going to weigh the water and the calorimeter. We're going to get an initial temperature for the water. We're going to weigh our salt. We're going to weigh a beaker. We're going to subtract the beaker from the weight of the beaker and salt. That will be the weight of our salt. We're going to then put the salt into the water, stir it around, get all the salt dissolved, and we're going to get a final temperature. Did the temperature go up or did the temperature go down? Come on, guys. This is not the hardest question I'm going to ask today. Did the temperature go up or did the temperature go down?
Did it go down?
It went down. So the sign when I subtract T final minus T initial, that sign is going to be negative. So literally speaking, my system, or excuse me, my surroundings have a negative energy. My surroundings lost energy. If my surroundings lost energy, then my system must have gained it. My system has a positive energy. It is endothermic in terms of my system because I have a positive energy. I have more energy after than before. The surroundings is exothermic because I have less energy after than before. So again, what I'm going to do is I'm going to first look at what's happening to my water. I have my mass of water. I have the temperature difference. And I also have 4.184. To get the water, I'm going to take my mass and my temperature difference, multiply it by 4.184. I get a negative 1600 joules. All right. I need to figure out what my Q of the dissolution is. It's negative the Q of the water. So if my water is negative 1600, my Q of dissolution is going to be a positive 1600 joules. Now, to get the enthalpy, the change in energy of the system per gram, that's not per gram, that's per gram. I have to determine how much salt was dissolved. So in this instance, what I'm going to do is I'm going to take the mass of my salt, divide it into my Q. So I'm going to get 1600 divided by 10.0, should be 0.6. Ultimately, it doesn't matter, but and I get 16.01 joules per gram. That is part B, ladies and gentlemen. Any questions here?
Yes. So regarding significant figures, how
Generally speaking. Okay, good question, Garris. Generally speaking, and this is just a general statement, you can look at the change in temperature. The change in temperature 90% of the time will dictate your significant figures. So yes, you're right, Garris. I'm wrong on my significant figures here. This should be 16 joules per gram because my temperature difference was two significant figures. Generally speaking, when you're doing these problems, you'll have 2 or 3 significant figures at the end, depending upon what your temperature difference is.
And then I have a question. Let's say you get a number like 1,000 where it's just zeros behind it, but you need to round to two significant figures. Would you want us to write it as like 1.0 times like 10?
That's
the
the
third.
easiest way. Darius,
Okay.
you have 2 ways to do it. That's the modern way to write it in scientific notation. The other thing you could do is you could put a horizontal line over the last significant figure. So
Okay.
in this instance, you would put it over the hundreds place.
Okay.
But I haven't seen that. The only time I see that, guys, is when I teach it. It's archaic and hardly ever used again. Are we good with part B? Are there any other questions on part B? Bethany just wants this over with. Thank you for being honest, Bethany. All right. The last part. In actuality, guys, when you're doing this in fall or spring, this is done in one period. And generally speaking, what I do in the summer is it's given 2 periods, but I tell the kids, okay, if you get this done, if you work efficiently, you can get it done in 1. And most people get it done in 1. The first part A, takes forever. It takes forever because you got to heat the metal up. Part B goes semi-fast. This one goes like this. All right. What we're doing in the third part is we're getting the enthalpy in kilojoules per mole of a reaction. So what we are going to do is we're going to mix 2 chemicals together and we're going to determine what the heat gained or lost of mixing those 2 chemicals is. Then we're going to figure out what our limiting reagent is, and we're going to divide by the limiting reagent, and that will give us our kilojoules per mole. Is this kind of making sense to you all? Okay, now, when I do my reaction, I'm mixing sodium hydroxide and HCl. There's a 1-to-1 stoichiometry between them. I have 0.100 moles of both of them. If I multiply this by 1/1000, I get 0.05000 liters times 2. That gives me 0.1. I also have 0.1 moles of NaOH. So each one is limiting. When I find the final heat of my reaction, all I got to do is divide it by 0.1 and I have the kilojoules per mole. All right. But this reaction is taking place in water. The sodium hydroxide has water in it. The HCl has water in it. Both of them contribute to the mass of the water. So when I'm going to get the final energy of my water surroundings, the mass of that is going to be contributed 50 milliliters from NaOH, 50 milliliters from water, from HCl. That gives me a total of 100 milliliters. I have to multiply that because the density of the salt solution is 1.02 grams per milliliter. So it's going to be slightly higher than 100 grams. Same thing. In this particular instance, I'm going to take the temperature of the NaOH before I mix them and the HCl before I mix them. Believe it or not, even in a room temperature, even if they've been sitting out, they will have different temperatures to them. So how you're going to get the initial temperature is you're going to take the two and average them. Then your HCl is going to be in your calorimeter. You're going to take your NaOH, dump it into the HCl, and you're going to measure the highest temperature that you reach. I don't know where I was going there. So I got my NaOH and HCl. My initial temperature is 23.3. My final temperature is 37.4. So to get the Q of my water, I take my 102 grams times the specific heat times the change in temperature. I end up with 6,060 joules. But notice, Garris, this has 3 sig figs. That ends up being 14.1. So that has 3 sig figs. This has 3 sig figs. But remember, my Q of water is negative the Q of my reaction because my reaction is my system. So if I had 60 joules for my water, my reaction equals negative 60 joules. Enthalpies are reported out in kilojoules per mole. So I have to change my joules to kilojoules, and I want it in kilojoules per mole. My limiting reagent was 0.1 moles. I divide the negative 6.06 kilojoules by 0.100 moles. My final answer is negative 60.6. That actually should be 60.6 kilojoules per mole. Any questions about the 3 parts, ladies and gentlemen?
Yeah, so earlier you were talking about atomic mass in part A.
That what part B?
Oh,
I'm sorry. You're correct, Garris.
okay.
If you get asked, if the question comes up, the formula for changing specific heat into atomic mass, you take the number 25 and divide it by the specific heat. That will give you your atomic mass, a roundabout.
Okay. But we don't have to have it on our data table?
You do if it gets asked for, Garris.
Okay.
At this point, I don't know. As I always do, Garris, I'm going to take you through the results in post lab in a second or two.
Okay.
I got some extra slides. I don't know what they're about. Yeah, do not worry if you get the PowerPoint, don't worry about the last 2 slides. What's going to happen after test 2 for my people? After test 2, we're going to get into this. For right now, you guys don't need to know these last 2 slides. It's something you should get to before the end of the semester, though. Any questions so far, guys? I'm going to stop share and hopefully get into the class list. Okay, before I go, let me just give you an idea, because this is kind of a little disruptive. The fact that we have a 2-lab class today. Right now you're caught up through the pre-lab for calorimetry. What you have due on Monday is you have the pre-lab for spectrophotometric determination of a dye. You have the pre-lab for that one due on Monday. Next Sunday midnight. Tuesday midnight, you have the pre-lab for thin layer chromatography, and you have the results for calorimetry, and the post lab for calorimetry. Then we're going to be back on our normal schedule. Okay. Now, generally speaking, you just turned in the gas law and the ionic compound today. Both of those were fairly easy, guys, weren't they? Weren't they fairly easy? Calorimetry is going to be hard. There's no doubt about it. As much as it may seem clear to you now, by the time you go to work it next Wednesday night at 10 o'clock, that was said sarcastically, guys. So when you go to work it, it's going to be a little fuzzy. So this one, I don't generally get good grades on. Spectrophotometric, it's an okay lab. It's not super hard. It's not super easy. There's a concept you have to grasp with that. Thin layer chromatography, super easy. Boiling point, easy. Vesper, easy. Then we have the final. The final, if you do a modicum of studying, I found that generally speaking, you do okay on it. Generally speaking, when I grade these things, I get probably an average of about 60, 65. And I get 1 or 2 A's, bunch of B's, bunch of C's. And there are those individuals that don't study and they blow the final. It's been my experience, guys, that the only way you can reduce your grade is to get something like a D on the final. That means take it seriously. I don't believe the final is that hard. I don't believe it's that hard, but when I say that, people tend to get overconfident on it and they don't study. The main way, I'm going to go through this probably later, but the main way I would study for the final, I would just go through and redo the calculations of the experiments you did. That would be the first thing I do. Then go and study a little bit of extra things on it. All right, now to get to today's post lab, and do I need to show you where the data is, guys? Are you pretty good with that so far? Anybody need for me to show the data? Hearing crickets, we're going to go on. So, calorimetry. Results. Preview. Okay, why am I not seeing it? I cannot figure out why that's not popping up for me. Ah,
Click bypass restrictions.
thank you. Apparently I've got something on there. Thank you very much. Is that Corey?
Kyle. Also, it may not do anything, so
Thank you.
I have no clue.
Okay, we can fix that. Sorry, guys. For some reason or other, I may not have opened it. Nope, that's good.
Click on submission views.
Submission. No, that's not going to do anything. This has to do after you submitted it, Kyle.
Gotcha.
Um, hmm. Let's try something else. Oh, wonderful. I can do the post lab anyway. Okay. Question 1 here. Simple. It's a simple reiteration of the metal. Nope. Oh, I'm sorry, guys. I apologize. I'm reading the problem and thinking it's a more complicated problem than it is. Basically, all you want, temperature change in water in the first thing. You know, final and initial temperature. Get that there. Change in metal. You're going to know what the initial temperature of the metal is. You know what the final temperature is. Okay. You have, okay, you have the specific heat of water, you have the temperature change of the water, and you have the grams of the water. Make sure you use grams of water and not the grams of the metal. You can use that information to tell me how much the water has gained temperature. Okay. Different numbers, guys. Are you noticing different numbers? So just because you know what the Q is here, don't automatically apply it here. You got to do a new problem. You're going to figure out the Q of the water, make it negative, and divide that by the weight of the metal and the temperature change of the metal to get the answer there. Questions about the post lab? And I'm sorry, I do not know what's going on with the results section. I have to call somebody. I'm glad I looked at it, so you're not going to find this problem out for you. I don't know what's going on with it. Sorry. Anybody have any questions? Basically, they're straightforward questions as I recall. I do not know why this is doing this. What do they say that an insane person is? They keep on doing the same thing over and over again, expecting different results. That's where I'm at right now. Okay, guys, I'm sorry, but I can't get you the results section here. Any other questions, guys? Got you out in less than an hour anyway.
Did you take roll?
Yes. I
Uh,
took him out for a pizza last night.
Did
bad
he mention
joke.
me?
Bad joke, bad joke, guys. We're good.
We're
We're
good as
good.
in I'm
Corey,
marked as
I've already
present?
marked you absent.
Okay, cool.
We're good. We are good. Everybody's good. I will figure this out, or more likely, the person that does technical support is going to figure this out for me. But I don't know why I can't access it. Okay, guys, I'm done. If you want to see me flounder around on my computer, you can stay here.
You have a good day.
You have a good day. Corey, you okay with it?
Yeah, I watched the video. It's looks decent.
You watched the video. Oh,
Mr.
I'm here. I'm here.
Can you check if you called on me for roll? I don't know if I got my attendance.
No, I know for a fact, Marvina, that I didn't call on you. I didn't call on anybody, Marvina.
Ah, okay.
Oh, okay.
Very funny.
I'm sorry. It's 8 o'clock in the morning. What do you want from me? So unless you have questions, guys, I'm done. I've got to go. I've got to get on to helpline to see what's wrong with the quiz.
Uh,
You have a good day too. Somebody have a question?
I do. Professor, it's Elaine. I was wondering if you had received my email for my lab.
Okay, email for your lab. What's this in regard to? First of all, when did you email it to me?
I
Yesterday
think
was kind of a lost cause.
I think it was last week because I couldn't turn in one of my lab notebook, and you said I could email it to you.
Yeah.
Okay, perfect. Thank you.
When did you email it?
I'm checking right now.
Because I don't recall seeing an email.
I believe I emailed it to you on June 16th.
June 6th. Okay. A week
16th.
ago?
Yeah, a week ago for
Okay.
my titration lab.
Okay, let's okay.
Yeah, because when I posted, I could only post a calculation and you only graded that. So
okay, so okay. Jeremiah, Paige, do you need anything?
Nope, I'm all set.
Okay.
Thank you, Professor.
Okay, 16th.
yes.
That looks good.
Okay. Okay.
That's Elaine, it's always good to check on it because sometimes okay. Why am I in this small? Oh, that's why. Okay, hold on a second. Okay. I'm not as a student. That's why it's so small. And no, it's so small because I made it small. Okay, this is why nothing occurred. Oh, never mind. It's down there. Paige, do you need something? Paige? Okay, Elaine,
Yes.
you have, in the conclusion, you haven't told me what the, is this the standardization of the base or is this the hydrotic acid? I'm sorry, the tablet. It's the
Okay.
tablet part. Okay. All right. You didn't tell me what the mass percent is. I know it's right up here. I know it's right. No, I know that's what it is. Okay, Elaine? But you gotta put it in the conclusion.
Okay.
First line, the mass percent of calcium carbonate in my antacid tablet was 53.47%. First line, put it there. Okay?
Okay.
Looking at this doesn't make sense to me. Because if you add too much of the hydrochloric acid, then you won't be pink. You'll be clear so that you will know that you have to add more base to make it pink. Does that make sense, Elaine?
Yes. I don't know why.
Okay, so that part doesn't make sense to me. All right, and look at this. The error analysis, Elaine, it says it could affect it. How is it going to affect it? Okay, the way it affects it is the heat turns the carbonate into carbon dioxide. I think they mentioned that in the handout. If it turns it to carbon dioxide, Elaine, you don't have as much carbonate. If you don't have as much carbonate, you're going to use less HCl, and in your final calculation, your mass percent of your calcium carbonate in the tablet is going to be reduced. Okay, so this is a good error. It's a great error. Okay, Elaine? But you got to tell me then what happens with the error. In this case, it reduces the carbonate in the that I have to titrate. That means I'm going to have less mass percent of carbonate in my tablet.
Yeah. Yes, it did mention in the handout.
Okay, you'll get a 7 on this, okay, Elaine?
Yes, thank you.
You're welcome.
Have a good day, Professor.
You have a good day too.